In this lecture, we will discuss the causality for LTI system and another property which is known as the stability for LTI system. We already discussed the theory part. Now we will discuss some problems related to this concept. We will verify whether the given LTI system is stable and causal. First, we will discuss some discrete time signal. After that, we will discuss continuous time signal. See, already discussed the concept. If you want to know more about the theory part, just watch the previous lecture. And here it is given h of n is equal to 2 raised to n into u of minus n. This is actually an impulse response of an LTI system, discrete time LTI system. See, this discrete time LTI system is characterized by its impulse response. If you know it's x of n and y of n, we can use the basic concept. But if h of n is given, we need to use the causality and stability condition for LTI system. So first we will check the causality condition. We'll verify whether the system is causal or not. Okay. To verify the causality, we know that h of n should be 0 for n less than 0. So that's a condition for causal. An LTI system is causal. So we need to verify this particular signal. Here it is given 2 raised to n into u of n. We know the signal u of minus n. U of minus n means the time reversed version of u of n, which is equal to 1 for minus n greater than or equal to 0. Or if you write in terms of n, you can see the n less than or equal to 0 if you multiply with minus 1. And 0 for minus n less than 0. And if you write in terms of n, it's n greater than 0. Means if you observe this particular graph, here it is n and this is 0, here it is 1, 2, etc. This minus 1, minus 2, etc. And u of minus n is equal to 1 for n less than or equal to 0. So this is a point 0. Okay. And if n less than or equal to 0 means towards left. That is from minus infinity to 0, the signal magnitude is 1 for this particular range. That is u of minus n. So we can see that h of n value is non-zero for this particular range. So we can conclude that the given LTI system is non-causal. So the causality condition is h of n is equal to 0 for n less than 0. But if you observe this particular waveform, here you can see that this is non-zero for n less than 0. So we can conclude that the given system is non-causal. Now we need to verify the stability condition. We need to verify whether the given system is stable or not. And for the stability, the before stability we can verify by using impulse response by using this formula. When n is equal to minus infinity infinity, modulus of h of n is less than infinity, we can say that the system is stable. That is absolutely summable. If this impulse response is absolutely summable, then we can say that the given system is stable. Now we can take the modulus and we can apply this sigma n is equal to minus infinity to infinity. In place of h of n, you can write 2 raised to n u of minus n. And we already written the definition of u of minus n. From this, it's clear that the signal exists from n is equal to minus infinity to 0, and u of minus n is equal to 1, and you can simply write it's 2 raised to n. Okay. And see, here the limit is from minus infinity to 0, but we know a formula for the infinite sequence for example, k is from 0 to infinity, a raised to k is 1 by 1 minus a if modulus of a is less than 1. And here the limit is from minus infinity to 0, so we need to change it to positive. Okay, so we can reverse this. For example, I'll give you a simple example. If n is from minus 2 to minus 1, a raised to n. Okay, if you expand this expression, you will get a raised to minus 2 plus a raised to minus 1, because n ranging from minus 2 to 1. The same expression you can write like this: n is equal to 1 to 2, or from 2 to 1, a raised to n, a raised to minus n, because in the first case it's simply n. In the second case, you can see that a raised to minus n. Both, if you substitute n is equal to 2, you will get a raised to minus 2 and a raised to minus 1. See, we can change the variable n to minus n by changing the limit also. Okay. So just as in the case of integration, you can change the variable from n to minus n. Okay, from this particular example, it's clear that you can change the variable n to minus n. At the same time, you can change the limit values also. And one more point, in the case of integration, if there is a limit from minus 2 to 2, and if you are changing this limit from 2 to minus 2, you need to put a minus I in the case of integration. But in the case of summation, if it's from n is equal to minus 2 to 2, you don't want to change any sign, you can simply write 2 to minus 2. Okay, it's a very important point. If it is an integration, you need to change the sign. You need to put an extra minus sign if you change the limit, order of the limit. But in the case of summation, you don't want to change any sign if you change the order of summation, because in the both cases you will get the same. Okay, and this n is equal to 2 to 1, you can also write like this, sigma n is equal to 1 to 2. But in the case of integration, if you change the limit, order of the limit, you need to put an extra minus. But in the case of summation, we can simply write this a raised to minus n itself. Okay, so please remember all these points when you do the problem. So you can change the sign. Okay, now you can see that it's from n is equal to infinity to 0 to raised to minus n. You can change the sign first, then you can change the order. Now it is n is equal to 0 to infinity 2 raised to minus n. 2 raised to minus n means you can write n is equal to 0 to infinity. It's 1 by 2 the whole raised to n, because 2 raised to minus n can be written as 2 raised to minus 1 the whole raised to n. So 2 raised to minus 1 means it's 1 by 2 the whole raised to n. So here a is less than 1, so you can apply this particular formula. And if you evaluate, you will get it's 1 by 1 minus 1 by 2. And from this, after simplification, you can see that it's simply 2. So it's less than infinity, so the system is stable. Okay, we already discussed the condition for stability. So the given system is non-causal and stable. Now we'll discuss another question. H of n is equal to 2 raised to n d of n minus 1. Here, first we need to verify the causality condition. We need to verify whether the given system is LTI system is causal or not. And for that, we need to observe the condition where h of n is equal to 0 for n less than 0. We need to verify this condition. And we know the signal contains two parts, 2 raised to n into u of n minus 1. So if you write the definition of u of n minus 1, which is equal to 1 for n minus 1 greater than or equal to 0, or n greater than or equal to 1, and 0 for n minus 1 less than 0 or n less than 1. And if you draw the waveform, it will be like this. For n is equal to 0, this is n is equal to 1, n is equal to minus 1, 2, minus 2, etc. And if n is greater than or equal to 1, this is a point 1, equal to 1, and greater means towards right. So at n is equal to 0, it's 0, minus 1, minus 2, etc. 0. This is u of n minus 1. If you observe the signal, you can see that for n less than 0, for this particular signal, n less than 0, the signal amplitude is 0. So we can conclude that the given system is causal, because here the response u of n minus 1 is equal to 0 for n less than 1. So we can conclude that given system is causal. Now we need to verify the stability condition, stable or not. For that we can use the condition, that is whether the given system is absolutely summable or not. So this is a condition we need to verify to check the stability. So you can write here n is equal to minus infinity to infinity. In place of h of n, you can substitute the signal, that is 2 raised to n into u of n minus 1 and modulus. And we know the signal u of n minus 1 this exists from 1 to infinity, starting from 1 and up to infinity. So you can simplify the summation from 1 to infinity, 2 raised to n, and u of n minus 1 is 1. And we know the formula for n is equal to 0 to infinity, or k is 0 to infinity, a raised to k is 1 by 1 minus a. Okay. And if modulus of a is less than 1, but here it is given it's greater than 1, means if you expand this you will get 2 raised to 1, 2 square, 2 cube, 2 raised to 4, etc., up to 2 raised to infinity. So if you expand this particular equation and if you add, you can see that it's a growing pulse, a growing system. So we can conclude that the given system, if you find this sum, it becomes infinity. It's not absolutely summable, not absolutely summable. So we can conclude that the system is not stable. It's not stable because we need to get a value which is less than 1. Here we will get it, which is equal to 1, equal to infinity. Okay. Now we'll discuss another question. Here h of n is given by 5 raised to n into u of 3 minus n. First, we need to check whether the system is causal or not. The condition for causality is h of n should be 0 for n less than 0. Now, if you observe the signal, there is two parts, 5 raised to n and u of 3 minus n. You can write the definition of u of 3 minus n. U of 3 minus n is equal to 1 for 3 minus n greater than or equal to 0. Or if you write in terms of minus n greater than or equal to minus 3, but we required in terms of n, so we'll multiply this quantity with minus 1. So now we need to change the sign. And similarly 0 for 3 minus n less than 0, or minus n less than minus 3, or you can write n greater than 3. And if you draw the waveform, it is 0, 1, 2, 3, it's minus 1, minus 2, etc. And if you observe this particular equation, n greater than or equal to 3 means this is 3, and if n is less than or equal to 3, sorry, n less than or equal to 3 means towards left side. Okay, that is from minus infinity to 3. The signal is having non-zero magnitude. And if you observe n, here it is n. If for n less than 0, the magnitude is 1. So h of n is non-zero. So you can write h of n is non-zero for n less than 0. System is non-causal. Okay. Now you can write the stability condition. In order to check whether the system is bivostable or not, we need to verify this condition, whether the h of n impulse response of the system is absolutely summable or not. That is, mathematically you can write the modulus, if you sum from minus infinity to infinity, it should be less than infinity. And you can substitute in this particular equation, n is equal to minus infinity to infinity. In place of h of n, you can substitute the signal, which is 5 raised to n into u of 3 minus n. So you can write 5 raised to n into u of 3 minus n. We know that u of 3 minus n exists from minus infinity to 3. Okay, and 5 raised to n. U of 3 minus n is equal to 1. And for the simplification part, we will split this summation, because we know the formula for n is equal to 0 to infinity, or then we need to rewrite this, or we can also write the definition for n is equal to 1 to infinity. Okay, and if this is 1 by 1 minus a, if it starts from 1 onwards, you can see that this is a raised to 1, a square, a cube, etc., up to infinity. So if you take a common, it becomes a raised to 0, a raised to 1, etc. So this equation you can simplify 1 by 1 minus a, because if n is equal to 0 to infinity, it's 1 by 1 minus a. So if it starts from n is equal to 1 onwards, you will write a into If n starts from 2 onwards, it's a square into. Okay. Now we need to rearrange this particular summation for non-equations. So first thing I can say that I can split the summation from minus infinity to 0. So if you split this summation, first we can write n is equal to minus infinity to 0, 5 raised to n. And it's very important when you write in the case of summation, if you consider the point 0, next value is 1. When in the case of integration, you can write minus infinity to 0 plus 0 to something. But if it is summation, it's a discrete values, the 0 is already considered in the first part. So we need to write n is equal to 1 to 3. That's the remaining part. So please remember this particular point is very important. When you split the summation or a discrete time signal, you cannot start from again 0. If you start again from 0 means you will consider that 0 value 2 times. So we'll write n is equal to minus infinity to 0 because 0 already considered in this particular first limit. Now we'll start from 1 onward. So you can split the entire summation like this. And we already discussed this n is equal to minus infinity to 0. And here the formula is for the positive value. So we can change n to minus n. So it becomes n is equal to infinity to 0, 5 raised to minus n, plus n is equal to 1 to 3, 5 raised to n. And again, if you write, we already discussed that we can change the order of summation, that is n is equal to 0 to infinity. Integration, if you write from minus t to t, if you change the order, you need to put a minus sign, t to minus t. But in the case of discrete time signal, if you write it from minus n to n, you can simply change it's from n to minus n. Okay. Here we need to put extra minus, but in the case of summation, we don't require any extra minus. So we can simply change the order. Now we can write 1 by 5 because 5 raised to minus 1, the whole raised to n. So 1 by 5 whole raised to n. And if you expand this, it's 5 raised to 1, 5 square, and 5 cube. 3 terms. Okay. And if you expand this, you will get, if you apply the formula, sigma n is equal to 0 to infinity a raised to k. This is standard formula. Can apply here. So you'll get 1 by 1 minus 5 plus, if you perform this, I think you'll get 155. And the first term is 5 by 4. Okay. So anyway, we don't need to calculate the final value, but we know that this is less than infinity. So the condition is valid here. So the given system is absolutely summable, or we can conclude that it's a stable system. Now we'll discuss another question. Again, it's very important. Here it is given e raised to minus 6 modulus of n. When there is a modulus of n, make sure that you are comfortable with this sign modulus of n. This is a discrete time sequence, and 1, 2, 3 here. It's minus 1, minus 2, minus 3, etc. When n is positive, so we can consider from 0 to infinity as a one group. You need to consider n as positive. Means you need to write e raised to minus 6 into n. That's the equation we need to use for the positive side. And for the negative side, you need to consider n as negative. So e raised to minus 6 into minus n. Okay, it becomes e raised to 6n. So from this particular point onwards, we know that it's a decaying signal. And here, in this direction, it's a decaying signal, e raised to 6n. Okay, you can try some values. If you're not comfortable with the waveform shape, you can just try 2, 3 values. At n is equal to 0, it's e raised to 0, that's 1. And after that, you can substitute e raised to minus 6, then e raised to minus 12, etc. Okay, here n is negative, so you can write e raised to minus 6. You'll get exactly the same value, but in a decaying nature. Now, if you observe the signal, you can see that the signal For the causality condition, we know that signal x is h of n should be 0 for n less than 0. But in this particular case, this question, h of n is non-zero in this particular question for n less than 0. That is some non-zero magnitude, that is it's 6 raised to n for n less than 0. So we can conclude that the given system is, this is a condition actually, causality condition. Now we'll verify here. So non-causal. Now we need to verify the stability. If the system is stable, it should be absolutely summable. Absolutely summable means modulus of h of n. If you find the sum from minus infinity to infinity, it should be less than infinity. We know that this signal is a converging signal in both directions. Definitely you will get a answer which is less than infinity, but we can try this because it's very important how to write the equation for this particular case. So if you write sigma n is equal to minus infinity to infinity, modulus of e raised to 6 modulus of n. So don't confuse with the two modulus. Here the magnitude is all positive values, so there is no importance for this modulus. And now we can split this because we need to use two different equation, and it's very important when you write it's from minus infinity to minus 1. So don't write up to 0 because this is a negative value. Only up to minus 1. From minus infinity to minus 1, n is negative. So first limit you need to write n is equal to minus infinity to minus 1 and e raised to n. For this duration, the signal magnitude is e raised to n. Plus, when you consider next value, you need to start from n is equal to 0 to infinity. That's a positive side. E raised to minus, sorry, I just missed 6 also. E raised to minus 6n. Okay, now we can apply the known theorems. We already discussed that if n is equal to 0 to infinity, a raised, if k is 0 to infinity, a raised to k is simply 1 by 1 minus a if modulus of a less than 1. And here, second case, k is equal to 1 to infinity, a raised to k means you need to write a into 1 by 1 minus a. Okay. And the first case, you can see that is from minus infinity to minus 1, but the formula is for positive values. So we can change the minus sign first. So you can write n is equal to infinity to 1. At that time, you need to put an extra minus inside the equation. Then equation will be equal. You can substitute n is equal to minus n. Okay, limit is now positive, but internally this n is now negative. Plus n is equal to 0 to infinity e raised to minus 6n. Now we can change the order of summation. We already discussed this type of problems. So now we can write e raised to minus 6n plus sigma n is equal to 0 to infinity e raised to minus 6n. Okay. And if you write the expression for the first case, you can see that it's e raised to, the first you can substitute the formula which is a into 1 by 1 minus a. If you substitute that, it's e raised to minus 6 by 1 minus e raised to minus 6. Plus for the second case, you can substitute the first formula, that is 1 by 1 minus a. 1 by 1 minus a. In place of a, it is minus e raised to minus 6. Okay, and if you simplify this, denominator is same 1 minus e raised to minus 6 and the numerator 1 plus e raised to minus 6. Definitely it is less than infinity. So you can conclude that the given system is stable because it's absolutely summable. The answer is less than infinity. Okay. Now we'll consider continuous time system. Here h of t is given by e raised to minus t modulus of t. First, we need to verify the causality condition. If a continuous time system, LTI system is causal, then its impulse response h of t will be 0 for t less than 0. Now we can, this is a condition. Now we can verify the signal h of t. Here this is the t is equal to 0, and here if you consider t is positive, because it is given e raised to minus 2 modulus of t, and if you consider the positive side, you need to consider t as positive. For the negative side, you need to consider e raised to minus 2 into t as negative, so you'll get e raised to 2t. Okay, so if you plot the signal, it will be something like this: a decaying signal in this direction, a decaying signal in the left direction. Okay, this is actually h of t. We already discussed a discrete time version. You can see the difference how we need to approach in a discrete time signal and a continuous time signal. Now if you observe the signal here, h of t is non-zero for t less than 0, so we can conclude that it's a non causal signal. For h of t is equal to e raised to 2t for t less than 0. Okay, now we can check the stability condition, whether the system is stable or not. For stability, for a continuous time system, we need to check whether it's absolutely integrable. So minus infinity to infinity, you can integrate the signal, and if you integrate the signal from minus infinity to infinity, you will get then we can verify if it is less than infinity. We can say that the given system is both stable or not. Now we can try here. Here we need to split the integration, because from minus infinity to 0, the signal amplitude is e raised to t, and if you put modulus, you'll get exactly same dt plus from 0 to infinity. So see the difference. If you use the integration, you can start from 0 onwards, but if it is a summation, you will write minus 1 and 0. So make sure that you are comfortable with this. Just refer the previous problem and this also. Okay, then you can see the difference. And here it is e raised to minus 2t into dt. Now if you integrate this, you can see that it's e raised to 2t by 2, uh, and the limit is from minus infinity to 0, plus second case e raised to minus 2t by minus 2, and the limit is from 0 to infinity. And if you apply the limit, you can see that the first case there is 1 by 2, and remaining time if you substitute, it's e raised to 0, okay, minus e raised to minus infinity, plus minus 1 by 2 into e raised to minus 2 into infinity, that is minus infinity minus e raised to 0. And if you substitute the values, e raised to 0 is 1, okay, e raised to 0 is 1, e raised to minus infinity is 1 by e raised to infinity, which is 1 by infinity, which is tending to 0. So you can write 1 minus 0 uh, plus minus 1 by 2 into e raised to minus 0 is 0 minus 1. Okay, again you will get 1 by 2. So 1 by 2 plus 1 by 2, which is equal to 1. And you can conclude that which is less than infinity, so system is stable. Okay, this is continuous time signal, and now we'll discuss one more problem in continuous time signal. Here h of t is given by e raised to 2t into u of t minus 1. First we need to check whether the system is causal or not. For causality of continuous time signal and for LTI system, causal LTI system should satisfy this condition: h of t should be equal to 0 for t less than 0. Now if you observe the signal, here you can see there is a term called u of t minus 1. U of t minus 1 is equal to 1 for t minus 1 greater than 0 and t greater than 1, and 0 for t minus 1 less than 0 and t less than 1. And if you plot the graph for u of t minus 1, this is 0 and this is 1. And if t is greater than 1, okay, from this particular point onwards, this is 1, the signal amplitude is 1. So signal exists from 1 to infinity, 1 to infinity. And if you observe the signal, here you can see that h of or u of t minus 1 is equal to 0 for t less than 0. So you can conclude that the given system is causal. And if you multiply with the e raised to 2t, you will get exactly the same 0 value for t less than 0. Now we need to verify the stability condition. For stability conditions of LTI system, we know that the impulse response should be absolutely summable. Uh, if you integrate it from minus infinity to infinity, it should be less than infinity. Now we'll try this. It's e raised to 2t into u of t minus 1. Okay, then I'll substitute here. It's from minus infinity to infinity e raised to 2t into u of t minus 1 dt. And you know to take the modulus also, but here the amplitude is positive. Then, and if you observe here, it's from 1 to infinity e raised to 2t, and u of t minus 1 is 1 dt, and it's e raised to 2t by 2, and you can substitute it from 1 to infinity. And if you substitute the limit e raised to infinity by 2 minus e raised to 1, and this e raised to infinity is tending to infinity, so your result is infinity. So system is not absolutely summable, and which is equal to infinity. So we can conclude that it's not stable. Not stable. Now we will consider another question. It's a slightly modified version of the previous question. In the previous question is e raised to 2t, now it is e raised to minus 2t. We already discussed u of t minus 1 is equal to 1 for t minus 1 greater than 0 or t greater than 1, and 0 for t minus 1 less than 0 or t less than 1. And this is a waveform we already discussed. This is 1 for 1 t is greater than 1, the function amplitude is 1. And definitely this signal amplitude 0 for t less than 0, because this u of t minus 1 is 0 for t less than 1. So we can conclude that the given system is causal because x is only the positive side. Now we need to verify stability condition. For verifying the stability condition, here we need to verify whether the impulse response is absolutely summable or not, the dt also. Okay, so you can substitute in this particular formula integral minus infinity to infinity e raised to minus 2t into u of t minus 1 modulus dt. Okay, this is positive values, then there is no need of modulus. And if you observe the signal u of t minus 1 exists from 1 to infinity, then the signal magnitude is e raised to minus 2t into 1. If you integrate it, e raised to minus 2t by minus 2, and you can substitute the limit 1 to infinity. And if you apply the limit, you can see that minus 1 by 2 outside, then e raised to minus infinity, because already there is a minus for t. If you substitute infinity, it becomes e raised to minus infinity, then e raised to minus 2. And we know that e raised to minus infinity is 1 by e raised to infinity, that is 1 by infinity, which is equal to 0. Okay, you can write 1 by 2, 0 minus e raised to minus 2. Okay, if you observe this, it becomes e raised to minus 2 by 2, which is less than infinity. So we can conclude that the given system is stable. Make sure that you are discussing about LTI system, don't get confused with the normal causality condition. If x of t and y of t are given, x of t and y of t relationship is given, you can approach the causal condition, normal causality condition. That is, it depends only on the present and past. That's a causal. And stability means it's a bistable, bounded input, bounded output. Now, instead of this relationship x of t and y of t, it's given h of t or h of n. If it is given the impulse response, you can verify whether the given system is causal by verifying the condition h of t is 0 for t less than 0, and our stability it's absolutely summable or not. Okay, thank you.